So let's bring actual logarithms into the problem now. So the whole thing about logarithms is they're inverses of exponents. And like we said earlier, the whole idea of inverses is if you've got something like, y equals 4x, to find the inverse, you swap x and y, and then solve for y. So y would be equal to 1/4 x. So these are inverses. So you could say something like f of x is equal to 4x. And then the notation they use these days, which I don't necessarily agree with, but the notation they use is -1 power. So the inverse of f of x would be 1/4 x. And then if you recall from algebra 2, anybody, was it algebra 2? When you do the composition of a function with its inverse, this is not something you really need to know. But when you do the composition of a function with its inverse, you're supposed to get x. So if we plugged this into this, if we said 4 times and we plugged in the inverse for x, 4 times 1/4, so we would get x. So anyway, that's just kind of a aside. But the point is you swap the x and the y. So our big problem is, okay, how do we find the inverse of something like y equals 2 to the x? Well, this is where they just kind of invented logarithms. And it's the notation that's weird. And I get this. And it's not an invention because I think math exists. It just had to be discovered. All right. So what they did was, this is base 2. So they said, all right, the inverse is going to be log base 2 of y is equal to x. So the exponent becomes the answer because that's what we're trying to solve for. The exponent becomes the answer. The exponent becomes the answer because that was the whole point. If you actually watch the first video, the whole point of inventing logarithms was to be able to solve for exponential functions when the variable is in the exponent. So what this does is this creates what I call the basic conversion. I'm sure there's a fancy name for this. I'm sure somewhere there is a fancy name, but this is the basic conversion. If I've got some logarithm, base A is equal to B. So we're going to convert back and forth between exponents and logs. So here's the way I always remember it. And this is really dorky, but so a logarithm is equal to the exponent. So this is the exponent. This is the base. See, that's the base. That's the exponent. So what happens is you just convert it. You say, okay, so that means a to the b power. And then the logarithm just drops off. So c is equal to a to the b power. So that's what we call the basic conversion, or I call the basic conversion. So we can run around all over the place. So log base 2 of 8 is equal to 3. That means that 2 to the third is equal to 8, which you all know is true. Now, the tricky part is when you have something like, oh no, what if I have 4 to the 1/2 power is equal to 2? How do I convert this into a logarithm? Okay, well, the base is 4, and the exponent is 1/2. See, logs are always equal to the exponent. The base is 4, and the base always goes here. And the log and the exponent is 1/2, which means logically the only place left for the 2 is like that. And I don't, I know this is the base, this is the exponent, this is the base, this is the exponent. I just don't know a fancy name for this guy. So for this guy. So what it amounts to is on worksheet 2, you're just going to be converting back and forth a lot between logs and exponents just to get the hang of it. So you're going to have things like, oh no, what is, this was a bad example. What is 12 to the 2 power is equal to 144. So that would become log base 12, and the exponent is 2. So log base 12 of 144 is 2. Or if you had, oh no, what is log base 5 of 25 is equal to 2. So that would just become 5 squared equals 25. So that's really all there is to worksheet 2 is you're practicing converting from exponents to logs or logs to exponents, because they're going to come up as a really, really, really big deal for the rest of the unit and the rest of the year, and you're going to need it next year, et cetera, et cetera.